Simple harmonic motion is the first of two applications that we see of differential equations in this core pure course. Now, simple harmonic motion is motion that can be governed by this differential equation. It is a second order homogeneous linear differential equation with constant coefficients, and it's written such that the coefficient of the second derivative is 1, and there is no first derivative term, and then this term here has a positive number as its coefficient. Okay, and there's it's homogeneous, so it equals 0. So the solutions of this are going to be x as a function of t, and we can use the auxiliary equation method to solve this differential equation. So let's use that. So lambda squared, if you're not sure about the auxiliary equation, check out some of my previous videos. So the auxiliary equation is lambda squared plus omega squared is equal to 0. And if I solve that for lambda, that's going to give me that lambda is either plus or minus omega I. Okay. Once I've got that these are a pair of imaginary conjugates, I can jump straight from those roots to the general solution of my differential equation, which is going to be some constant times the cosine of omega t plus b times the sine of omega t. Okay, and this is the general motion solution of the simple harmonic motion equation. If we're given more information, we'll be able to calculate values for a and b in a particular scenario, and obviously omega given as well. That's usually given in the differential equation at the top. But using A-level maths methods, actually, we can write this in a different form. We know that two sine waves like this can be written as a single cosine function, omega t plus some phase shift, or you could, if you wanted to, write it as the sine function, of course, omega t plus, I'm going to call it delta. This form is really useful if you're given the initial conditions, because A would be the initial displacement, and B would be related quite easily to the initial velocity. But if you want to get an overall picture of the overall motion, then these two are quite useful because it gives you the amplitude of the motion, r. So it depends on what you're working with. Usually on this course, we will stick with this top one. So that's what I'm going to be using in today's video. A couple of things I want to mention about this differential equation. If you do an online search for SHM, then you might find an equation for the velocity. So I'm going to derive that one here, although you don't need to know the derivation of that for the A-level further mathematics course. What we can do is we can take d2x dt squared, and I can write that as dv by dt, because that is what d2x dt squared is. And using the chain rule, I can say that is the same as dv by dx times dx by dt. Okay, and then we know that dx by dt is v, so that becomes dv by dx times v. So this is the same as the acceleration. So if I put that into here and then solve that differential equation, I can get v in terms of x, which is an equation that quite often pops up in simple harmonic motion equations theory. So dv by dx times v, so that's my acceleration, plus omega squared x equals 0. This is now a differential equation, first order differential equation with separable solutions, and if I solve that, and then actually I need to times the equation by 2, but I can end up with v squared is equal to omega squared x, minus omega squared x squared plus a constant. And what you'll come to find is, as we study simple harmonic motion in a little bit more detail, then the velocity, or x dot, is 0 when x is at its maximum. Now, in simple harmonic motion notation, we tend to use a as the amplitude of motion, so it's not the acceleration, so just be careful with that. This is why we tend to stick with x dot and x double dot for the derivatives. But if we use this condition, then that will give us the famous velocity equation from simple harmonic motion as being v squared equals omega squared into a squared minus x squared. And we can see that V is 0 when X is A or negative A. So that's the two extreme cases. And it's at X maximum when X is 0, which is the center of oscillations. The other thing I want to mention is the period of the motion. So if we look back at the general solution here, this is a periodic function, i.e. it repeats, and the period is how long it takes before the system is back to the start again, or how long it takes to repeat its motion again. So we know that the period of a regular sine wave is 2 pi, but we've got omegas in there as the coefficients of t. Omega is a constant, but it does change the period. So the period is t is equal to 2 pi divided by omega. Okay, so if you think about the sine wave, then you can take any point on the sine wave, say here, and when you get to the same point again in the next phase, before it starts repeating again, then that distance there in time is t, this period of motion, if you like. Okay, that's the t-axis, and that's the x-axis. Okay, and it's calculated as 2 pi over omega. So if omega was 2, for example, then that would take pi seconds to get from here to here, or indeed any other point on the curve to the next point in the same part of the phase, the movement. Okay, so occasionally a question will ask about periods, in which case that is the formula you need to use. Okay, so that's the general theory of simple harmonic motion. The rest of this video, we're going to look at one example, which is a particular case, a particular physical case that uses simple harmonic motion, and it is the horizontal spring mass oscillator. We're going to look at the vertical spring mass oscillator in the next video. That's a little bit more complicated, but for now we're just going to look at this simpler case. So what this situation uses is it uses something called Hooke's law. Now, Hooke's law is not something you need to know for the core pure course. However, it's quite a basic law, you might have come across it anyway. And it essentially says that the tension in a spring is equal to a constant times x, which is where x is the extension of the spring. So what that means from a modelling point of view is if you've got a natural length of a spring, say 10 centimetres. If I extend it to 12, that's got an extension of 2, so x would be 2. That would have some force on it, depending on how powerful the string is, which is what k represents. But if I double that extension to 4, then that's double the force. Or if I triple the extension, that triples the force in the spring. That's what Hooke's law says. There is a limit to that. It deforms if x gets too big, but on this course we just keep it simple, and we only will have situations where the tension is proportional to the displacement from the natural length. Okay, so this equation here. All right, so what I can do is, just like in any mechanics setting, I can take my mass and I can do put all the forces on and do a F equals ma. So the only force acting on it is going to be the tension, okay, because the table will be smooth, otherwise it wouldn't be SHM, there'll be some damping involved, which we'll look at later. And I'm also going to say that wherever the kind of equilibrium point is, whenever the tension in the spring is 0, that is when x is 0. So I'm defining x to be positive to the right. Okay, so if it's being pulled that way, then the spring is going to pull the mass back that way. And also, because it's a spring, if I push the mass such that x is negative, then the spring will be in compression and it will be pushing the mass back that way again, which is what gives us this kind of bouncing motion, okay, because the spring can push back. So that's the only force that we care about. Obviously it's got its weight and its reaction force, but that's not in the direction of motion. So if I use F equals ma now on this situation, then I'll end up with minus t, which is kx, and it's negative because it's acting to the left when positive is to the right. That's going to equal the mass times the acceleration, but the acceleration by definition is x double dot. So that is then what F equals ma looks like in this situation. And then what I can do is I can write that as x double dot plus k on mx equals 0. And because k and m are both positive, that means that this is x double dot plus a constant, positive constant, times x equals 0. So this is exactly the form of the simple harmonic motion equation. Okay, so that's SHM. And in this case, we can extract the value of omega as being k over m. Okay. Now that we've got values of omega, we can spot them. You don't even have to do the auxiliary equation for these questions. You can just jump straight from the values of omega to the general solution. So we know that x is going to equal some constant times the cosine of the square root of omega, which is k on m. Oh, sorry, that should be omega squared. It's k on m. The square root of k on m t plus b times the sine of the square root of k on m t. Okay, so that's the general solution, and it's just going to be some kind of sinusoidal function where a and b depend on the initial or boundary conditions, how the problem starts. Okay. All right, so let's have a look at a numerical example of this. So we've got a particle of mass 10 kilograms that's resting on a smooth horizontal table. So I did mention it has to be smooth, otherwise you've got a frictional force which is going to dampen the motion. A string of natural length 0.3 meters is attached to the particle at one end and to a vertical wall at the other end. You may assume that the spring is light and horizontal. Okay, so exactly the same situation as our general case just a second ago. We're told that the tension force in this spring for an extension x meters is 100x newtons. Okay, so we can see that the tension force is proportional to K times the extension. So this is following Hooke's law. Let's take the equilibrium point of our system as being here, and I'm going to find that as being x. Okay, so my variable x is going to start from 0 here and increase to the right, such that this distance here, that's from the wall to that x definition, that is L0, which is the natural length of the spring. So if the system was at rest, then and not moving at all, then that's what the spring would, that's where it would be. If it's anywhere else, then there'd be some kind of resultant force on the mass, which would start the SHM. Okay. Now we are told that the natural length of the spring is 0.3 in this case, so we can actually replace that with a 0.3. And now we are told that the particle is placed at a distance of 45 centimeters from the wall and released from rest. So this mass here is pulled to the right such that the distance from here to here is 0.45 meters. Just be careful, you've got to keep the same units. Okay, that's in centimeters, that's in meters. So just make sure you're paying attention to the units, which means that at that point, x is 0.15. Okay, x is my variable, but it's defined from the equilibrium, not defined from the wall. So just make sure you're paying attention to what's going on in terms of the variables. Okay, let's get down to the question. Okay, part A, derive a differential equation to model this situation. Part B, solve this differential equation, stating x as a function of t. Part C, state the amplitude and period of the motion, and then sketch the graph. And then finally, part D, find the time that the particle is less than 20 centimeters from the wall before it returns to its starting position. Okay, so let's start with part A. So to answer part A, to derive the differential equation, let's consider this mass, which has got a mass of 10 kilograms. It's got the force acting on it, which is 100x. Okay, that was given in the question. and this is my positive direction to the right. Okay. So using F equals ma, I get minus 100x, and it's negative because it's acting in the opposite direction to my positive, is equal to the mass, which is 10, times the acceleration, which by definition is x double dot. And so that's going to give me my governing equation as being x double dot plus 10x is equal to 0. Okay, so that is my governing equation, my differential equation, to model this situation. Okay, part B. Solve this differential equation stating x as a function of t. So to answer part B, I'm going to notice that omega squared is 10, and that tells me that omega is root 10. Now that I've got omega, I can actually just state my answers. Okay, so my answer to this is x is going to equal some arbitrary constant times the cosine of the square root of 10 times t, plus b, some other constant, times the sine of the square root of 10 times t. Okay, now I can use my conditions in the question. So in the question, I'm told that the particle is placed at a distance of 45 centimeters from the wall and released from rest. So it's initially at rest, which means x dot is 0, and it's initially at a displacement of 0.15. So my conditions are when t equals 0, x equals 0.15, and x dot is 0. Okay, those are my conditions that I'm going to use to find values for capital A and capital B. So if I use 0.15, I get 0.15 equals A. And if I use x dot at t equals 0 is equal to 0, that's going to give me 0 is equal to, that will disappear because that'll be a sine. It's this one here that's going to be b times the square root of 10. Okay, when I differentiate it, and that tells me that b is 0. So putting those together and putting them back into here, that gives me my particular solution as being x is equal to 0.15 times the cosine of root 10t. Okay, that's my answer. Okay, part C. State the amplitude and period of the motion, sketch the graph. Okay, so for part C, well, the amplitude is easy because that's just the coefficient of my cosine function. So the amplitude is 0.15, and the period of my motion, I think back to my general formula, it was 2 pi divided by omega. So in this case, that's 2 pi divided by the square root of 10, which I can write as pi root 10 over 5. And if it asks for a numerical answer, then I can give it to 3 sig fig. But root 10 pi would be fine for a corporeal paper. If this was mechanics, then that would be to 3 sig fig for sure. 1.99, there you go. So that's 1.99. And because the length is all in meters and the mass was in kilograms, then this is seconds. Okay, SI unit. Okay, also wants me to sketch the graph. Well, it's just sketching this. So that's going to have a maximum to start with because it's a cosine curve, positive cosine curve. It's just going to be a cosine curve. It's not particularly taxing to draw. You should do at least one period. I would be inclined to do a little bit more than a period, just to illustrate what's going on. T-axis is horizontal, x-axis is vertical, because x is a function of t. And then just pop some points on. So we know that's 0.15 up there. We know it's going to be minus 0.15 down there. And let's pop this one on here. That's 1.99. That's what we calculated here. So something like that, that'll be all right. Okay, and finally, part D of my example. Find the time that the particle is less than 20 centimeters from the wall before it returns to its starting position. So, less than 20 centimeters to the wall means that x is less than negative 0.1, because x is 0, is 0.3 from the wall, and if I increase x, that's going to move it further away from the wall. So I need to decrease x from 0 to get it closer to the wall. So I'm looking for values of x as being less than 0.2. That's the information you need to extract from that side of the question there. So for part D, less than 20 centimetres from the wall, that implies that x is strictly less, although it doesn't actually matter, negative 0.1. Okay. So, looking at this graph, we can see that there are times when it's less than negative 0.1, and it's going to be between here and here. So now this just becomes a trig equation question. I need to find this value here of t1, this value here of t2, and the time in between those two times is when it is less than 20 centimetres away from the wall. Okay. So how do I solve that? Well, the first t value is just nice and easy. I just plug in x's minus 0.1 into here and then solve. So I'm going to get, I'm going to write this as 1 divided by the square root of 10 multiplied by the inverse cosine of, and then that's going to be minus 0.1 divided by 0.15. That's going to give me my first t value. Do make sure that you are in radians. You have to be in radians for this because we are using calculus on trigonometry. Okay, it's differential equations. So if you're in degrees, you will get a wrong answer. You must be in radians. And that's the first time. That's t1 0.727, and that kind of fits with that being about 2. So that's good enough for me. So t1 equals 0.72748, blah, blah, blah. And then to get t2, well, there's different ways you can do it. This isn't kind of A-level maths. This is further maths. So I'm just going to crack on and just write 2 pi minus, and then stick another bracket on the end. Don't forget the root 10 needs to be divided after you've done that process. So 1.2594 is t2. And then I'm looking for the time, total time that it is closer to that. So I need the difference between them, and that'll be my answer. So delta t, and this is the one I'm going to write to three significant figures. I'm going to subtract 0.72748 from that, and leave my answer as 0.532. And again, that's in seconds. There we go. Okay. So that time difference there is slightly over half a second. Okay. Okay, that answers the question. Yeah, that's it. Okay, fantastic. Thank you very much for watching. And if you have any questions or anything I've said, please just drop a question in the comments and I'll get back to you when I can. In the next video, as I said, we're going to look at the vertical spring mass oscillator.